Okay, good evening. So, to my students who missed the face-to-face class, I will be discussing module number 1. And the first topic is digital systems and binary numbers for section 1.1. Our objectives in this subtopic is or are the following: to be able to convert binary, octal, hexadecimal, or any base to decimal number system, and vice versa. And then to solve for the complements of numbers. Then to solve for problems related to binary numbers. Convert different binary codes. And then to sketch the output of the basic logic gates. Let's go to the main discussion. So the signals in most present-day electronic digital systems use just two discrete values and are therefore said to be binary. We define bit is a binary digit, or bit is a shortened term for a binary digit. B is for binary and IT is for the last two letters of the word digit. So binary digit is shortened to the word bit. A bit has only two possible values, which is 0 and 1. Binary codes. These are discrete elements of information. Binary codes are discrete elements of information represented with groups of bits. For example, number 7 in decimal is represented by binary code 0111. So it is a representation of something by just the grouping of bits. We add base for distinction of the number system. For example, we put the base 2 to indicate in this expression 0111 base 2. We add 2 the subscript 2 to indicate that this 0111 is in binary system. And then here 0111 to the base 10, we add the subscript 10 to indicate that this number is in the decimal system or base 10. And then that's it. Discrete quantities. Discrete quantities are from naturally discrete data or quantized from continuous process. When we say quantized, what does it mean with this word quantized? In digital electronics, quantizing means we take samples of the analog data, of the continuous data. We take samples, and so the result is we get discrete samples or number of data. Examples of this are the payroll schedule, which is inherently discrete since it contains employee names, social security numbers, weekly salaries, income taxes, and so on. So where was I? Going back. Example of discrete quantities are the payroll schedule, and then another is the tabular data, which represents specific quantities being recorded by a research scientist. And there are a lot of other examples for this discrete quantities. In many cases, the quantization of a process can be performed automatically by an analog to digital converter, or ADC. If we're talking about electronic circuits, but there are general types of circuits. We have analog and digital, but there are still other types of circuits aside from analog and digital, like mixed circuit, which is a combination of both analog and digital circuits. And we even still have RF circuits. But if we talk about quantization, I'm not sure this. If we talk about quantization, or the sampling process, the usual circuit used for this is the analog to digital converter. Yeah. From the definition, it is a device that forms a digital or discrete representation of an analog, which is a continuous quantity. So it converts the analog or continuous data into digital, which is discrete data. HDL. What is a hardware description language? An HDL, or a hardware description language, describes and simulates the functionality of a digital circuit. From the word itself, hardware description language. So we are describing the hardware. This is not the same with C, but we have programming languages like C. Change the size. Like C++, Java. These are programming languages. Defines the software. But HDL, or hardware description language, we define the circuit. So we design, in short, we are designing the circuit, but instead of placing the components in a schematic, we are using text. This is text based. We have HSpice, which is also text-based, but it is used to describe circuits which are analog. HDL describes circuits which are digital. With the use of logic gates, we are using logic gates. So that's the difference between HDL, or a hardware description language, and other programming languages like C++ and Java. And the difference also from HPice and other text-based design tools which describe the circuits in analog form. HDL is for designing circuits in digital form. An HDL resembles a programming language and is suitable for describing digital circuits in textual form. We will discuss this later more in section 1.4. Let's go to the number system. Decimal 7392 is a shorthand notation for what should be written as. We can write 7392 for the decimal 7392, we can write it as 7 times 10 to the power 3 for 7000, and then plus 3 times 10 to the power of 2 for the 300, plus 9 times 10 to the power 1 for 90, plus 2 times 10 to the 0, and this is equal to 1 for 2. Thus, 10 to the power 5, a sub 5, etc. And for the decimal point, the exponent of 10 becomes negative. And from the example, 7392 RA3, this is the general form of a decimal number, expanded form. RA3 is 7, so 7 times 10 to the 3. Excuse me. And then A2 is 3, A1 is 9, then A0 is 2. We don't have a decimal point, a decimal number after 7392, so we don't have A sub -1, A sub -2, and so on. Decimal is base or radix 10. It uses 10 digits, and coefficients are multiplied by powers of 10. For decimal, the base is 10 and the digits are from 0 to 9. So we have 10 digits. How about for binary? For binary, this is base 2. Digits are 0 and 1. So we have 2 digits, 0 and 1. What are the other? Hexadecimal, base 16, we have digits, 16 digits, so from 0 1 up to 15. Or no. This is for the decimal equivalent, but the digits are actually 0 to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then A, B, C, D, E, F. Those are the 16 digits of hexadecimal of the hexadecimal number system. For octal, this is base 8. So we have 8 digits. 0 to 7. Let's go to converting any number system to decimal. There are many different number systems. In general, a number expressed in base R system has coefficients multiplied by powers of R. Just like in our previous example, for the decimal, the powers are 10. Because our R is 10, that's our radix or base. For binary, our R is 2. For hexadecimal, our R is 16. Let's have an example in converting from binary to decimal. How do we convert this binary number into a decimal? Using this formula, our base for the binary is 2. So we multiply, we use this formula, general expression. Replace R with 2 and AN by the digits. Let's write this down. One 0 1 0 1 1 1 0 1 0 dot 1 1 base 2. What is this in decimal? So let's write first the powers of the exponent. The exponents are 0, 1, 2, 3, 4, and then for the decimal numbers, -1 here, -1, -2. So 1 times 2, the base is 2, to the fourth, plus 1 times 2 to the 3, plus 0 times 2 to the 2, then to the 0 again. This corresponds to this corresponds to this, and this 0 corresponds to this 0, then 1 times 2 to the power 1. These are the exponents. Don't forget that these are the exponents that we placed here. And then this ones and zeros is what we multiply to the radix that is being raised to the exponent. So plus 0 times 2 to the 0 plus 1 times 2 to the negative 1 plus 1 times 2 to the negative 2. This is 16, 2 times 2, 4 times 4, 16 plus 8 plus, this is 0, 0, so plus 2 plus 1 times 2 to the negative 1, this is 1/2, plus 1 times 2 to the negative 2, this is 1/4. So what is this? How is this? 16 plus 8 plus 2, that's 10, so 26. 26 point, that's 0.5 plus 0.25. 26.75. This is the base 10. This is the decimal equivalent of the binary number 11010.11 base 2. It's equal to 26.75 base 10. So that's how you convert a binary number to decimal. We have another example. If we convert 4021.2 base 5, what is this in decimal? Same. You just multiply each digit by the radix. Here, the radix or the base is 5, and we raise it to the power of the exponent. For example, we just need to know what exponent we should multiply, and we should raise the base. For 1, must be 1 times 5 to the power 0. So 0, 1, 2, 3. So we have 0, 1, 2, 3. Then for 2, that's negative 1. So 2 times 5 to the power negative 1. If we evaluate this expression, the result is 511.4, and the base is 10. 511.4 base 10. The letters of the alphabet are used to supplement the 10 decimal digits when the base of the number is greater than 10. For example, for hexadecimal, the base is 16. But for decimal, we only have 9 digits from 0 to 9. So what are we going to assign for the other digits of the hexadecimal number? Let's take a look at this table. These are the most common number systems: decimal, base 10, then binary base 2, octal base 8, then hexadecimal, which is base 16. Let's start with the hexadecimal. Base 16, well, we need 16 digits. The equivalent of this 16 digits is 0 to 15 for decimal. 0 to 15. For hexadecimal, we use 0 to 9 and then A, B, C, D, E, F. Because it needs 16 digits. So we used the alphabet, the first 6 alphabet letters, A, B, C, D, E, F. For octal, the base is 8, and we only need 8 digits, so we have 0 to 7. It just included 0 to 7. 7 is the maximum for 1 digit octal number. After that, if we increment this with 1, so it will go to the next digit. Becomes 10, which is 8, which is 8 in decimal. So you need to know how to count. You need to memorize this conversion between different bases of the number system from 0 to 15. How do you count? You need to know how to count from the different number systems. For example, for binary, you start with 0. Let's count in binary. 0, 1. What's next? Since binary has digits 0 and 1 only, so the first digit is already full, we go to the next digit, so it becomes 10. Next, we add 1, so 10 plus 1 becomes 11. Next, we can't fill in here anymore because it's already full. 1 is full, so we add 1, becomes, we go to the next digit, becomes 1, 0, 0. Next, add 1, we increment the least significant bit, becomes 101. Then it's already filled, we increment the next digit, so 1, 1, and then 0. Next, it's 1, 1, 1. What's the next after this 111? Binary number. Since we can't add another 1 in these 3 digits of the binary number, we go to the next digit, becomes 1, 0, 0, 0. So that's how you count in binary. You just add 1, start adding 1 to the least significant digit, and if it's already filled, you go to the next higher digit. So 0, 1, 1, 0, 1, 1, and then 1, 0, 0. This is 1, 0, 1, then 1, 1, 0, then 1, 1, 1, then 1, 0, 0, 0. The equivalent of this in decimal is, we have digits from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8. So this is 0, this is 1, 2, 3. So this is 3 in binary. This is 4 in binary. It's 1, 0, 0. This is 5 in binary. This is 6 in binary. This is 7 in binary, and this is 8 in binary. For example, for 6 base 10 is equal to what in binary? It's 110. In binary, you can check with your calculator. It has a conversion, number system conversion with your FX991 ES Plus calculator. Try to explore how to do this, how to do number conversion with your calculators. So memorize this table. For example, 15 decimal 15 is 1111 in binary. Then this is 717 in octal. And then F in hexadecimal. Hexadecimal to decimal conversion. Let's have an example here. B65F base 16 is equal to what in decimal or base 10? So same with our previous examples, we just multiplied the digit with powers with base 16. So the exponent here is 0. For F, it's 0. Remember that F is 15 in binary, in decimal. So instead of writing F here, it wrote 15. 15 times 16 to the power 0. And then 5 times 16 to the power 1. So 0, 1, 2. So 16 to the power 2 times 6. And then 0, 1, 2, 3. 16 to the power 3 times B. But B is 11 in decimal. Because diba 0 to 9 and then AB. A is 10 and 11 is B. It's also nice if you can memorize powers of 2. For example, 2 to the power 7 is 128. 2 to the power 10 is 1024. To the power 2 to the power 12 is 4096. Let's go to binary addition, subtraction, and multiplication. How would you perform addition in binary? Perform subtraction in binary and perform multiplication in binary. It's the same. The process is the same. For example, 101101 101101 plus 100111 100111. Let's determine first how to add with single digits. 0 plus 0 in binary is 0. 0 plus 1 in binary is 1. Then 1 plus 1 in binary, that's in decimal 1 plus 1 is 2. But 1 plus 1 in the equivalent of decimal 2 in binary is 10. This will only become 1 if we have 3 ones to be added. So if 1 plus 1 plus 1 is but this is 3, number 3 in decimal. 1 plus 1 plus 1 is 3 in decimal, but 3 in binary is 1 1. Let's check. 3 in decimal is 1 1 in binary. So we already know the addition in binary for single digits. Let's add these numbers. So 1 plus 1, 1 plus 1, this is 1 0. So 0 carry 1. So 1 plus 1, this is 1 0 carry 1. So 1 plus 1 plus 1, this is 1 1. Carry 1, so 1 2 0 carry 1. It's 1, then 1 plus 1, 1 0. Therefore, the result is, let's group this by 4. 1 0 1 0 1 0 0 base 2. 1 0 1 0 1 0 0 base 2. Let's check. 1 0 1 0 1 0 0. That's right, yeah. Subtraction. Well, subtraction is easy if the minuend or the upper number where we are going to subtract is bigger compared to the subtrahend. Just like in this case, 101 101 is a bigger number compared to 100 111. So we can subtract easily. 1 minus 1 0, 0 minus 1, so we need to borrow 1, becomes 1 0 minus 1, that's 2 minus 1 is 1, and this becomes 0 since we borrowed. So 1 0 minus 1 1, then this becomes 0 since we borrowed, so the rest will be 0. Multiplying binary numbers is the same with the usual way that we multiply numbers in decimal, except that this is much simpler because you're only dealing with ones and zeros. Now let's go to converting decimal to binary or binary to decimal. No, converting decimal to binary. In converting, how do we do this? How do we convert a decimal number to binary? We just divide by 2 the number. Divide by 2 in succession. Get the remainder to determine the binary equivalent. For example, 41. We want to convert the number 41 in decimal to its binary equivalent. So we divide 41 by 2, then get the remainder, then continue the process until we reach the quotient of 0. 41 divided by 2, that's 20, remainder 1. Remainder 1. Then 20 divided by 2 is 10, remainder is 0. Then 10 divided by 2 it's 5, remainder 0, and then 5 divided by 2, it's 2, remainder 1, then 2 divided by 2, it's 1, remainder 0, then 1 divided by 2 is 0, remainder 1. So we take the remainder. The remainders are 1, 0, 0, 1, 0, 1. 1, 0, 0, 1, 0, 1. And then we read the remainder down to up from the last remainder to the previous. So we start reading from the latest. So 101, 001. Therefore, the binary equivalent of 41 base 10 is 101, 101, 001 base 2. In general, conversion from decimal integers to any base R system is similar to this example, except that division is done by R instead of 2. So we can easily convert a decimal number or integer to any base by dividing with the base. For example, we want to convert 23 base 8 to decimal. So we divide 23 with the base, which is 8. Then we take the remainder. That's 8/16. So it's 2. 16, so 4, remainder of 7. Remainder. Then 2 divided by 8, that's 0. Remainder. Then from the latest to the oldest, therefore 23 base 8 is 27 base 10. Check from your calculator. You can check from your calculator whether this is correct. Try. Next. Let's go to the complements of numbers. Complements, this simplifies the, by the way, the reference of my modules is from the book by Morris Mano. Complements of numbers, this simplify the subtraction operation for logical manipulation in digital computers. This makes it simpler and less expensive to implement the operations in the logic circuits. So what are the complements of numbers? There are two types of complements for each base R system. The R's complement or the radix complement and the R-1's complement or the diminished radix complement. For example, for base 2 or binary, we have the 2's complement and the 1's complement. 2's complement is the radix complement We just replace the r with the base, which is 2. And then the r minus 1, so 2 minus 1 is the 1's complement. This is the diminished radix complement for the binary system. For decimal or base 10, the r's complement becomes the 10's complement, and the r minus 1's complement is the 9's complement.